Alright, now it's time for Lecture 6 on gamma decay for Chemistry 312, Radiochemistry. This lecture is in two parts. The readings for this lecture are Modern Nuclear Chemistry, Chapter 9, and Nuclear and Radiochemistry, Chapter 3. This lecture is going to be in two parts. The first part is going to cover energetics related to gamma decay, the types of gamma decays, transition probabilities, what percentage of the time a gamma occurs. We'll also discuss internal conversion and angular correlation of gamma emission. In other words, if you could align the nucleus, certain nuclei properties would dictate that certain gamma lines will emit in defined angles. So gamma decay is the emission of a photon during the de-excitation of a nucleus. There are a wide range of energies and different yields from virtually 0 to 100%. We've already discussed isomeric states, and here's an example of an isomeric state, zinc 69M, where it has an excited nuclear state. So an isomer, as we discussed earlier, are two different configurations of the same isotope. They have different total angular momenta and different energies, right? The spin and parity of the ground state and the isomeric state are different, and they have different energies, one being the ground state. So the decay from a ground state to a progeny state would have a different energy from the decay of the isomeric state to the progeny state. And since they're at different spin and parities, for instance, this excited metastable zinc 69 has a spin and parity 9/2 plus, the ground state 1/2 minus, large spin difference, parity flip, highly forbidden, just like in beta decay. Then a small percentage of this metastable state decay by beta, either by emission of a photon to the ground state, and that occurs 99.967% of the time. A small percentage of the time, shown here as 0.33%, the excited isomeric state will beta decay directly to the progeny isotope. And as you can imagine, it would most likely decay to different states through the beta decay from the ground state, since it's going from 9/2 plus. In this case, it goes to a 5/2 minus state, whereas for the ground state of the zinc 69, it's 1/2 minus. It primarily goes to the 3/2 minus ground state of the gallium. And this decay from metastable state to the ground state is called an isomeric transition. And gamma decay energies range from a few keV to many MeV. One of the things that we're interested in evaluating in gamma decay is we need to understand what percentage of the time does a gamma occur. And we'll go over this with an example with europium-152. We've already discussed this in class where we talked about reactions where gamma decay can be used as a way of determining the concentration or the activity of an isotope. And you have to know what percentage of the time this gamma occurs with the decay. With europium-152, there are many different gamma decays. And actually, if we look at the europium-152 here, we see that it actually decays by electron capture and beta decay. There's also some metastable states. These isomeric transitions also occur, which are shown here. We're going to ignore those for now. But let's focus on trying to evaluate the gamma decay from europium-152. It's complicated because there's two different routes. There's an electron capture and this beta decay. So as an example, let's try to figure out what are the major gammas that would be expected from the decay of europium-152, and then the percentage of those times those gammas are going to occur for each decay. And if you go to the chart of the nuclides, you'll see that there's three gammas that are listed for europium-152 decay. They're shown here, the 121, 1400, and 340 keVs for the decay of europium-152. Now if we look at some table of the isotope data, and we can get percent yields and transitions for gamma decay from this data, we see here's europium-152 decaying by beta emission, going to gadolinium-152. And from the table of the isotopes, we know, the chart of the nuclides, we know that there are 3 main gamma decays. And if we explore the data as we've shown in the table of the isotopes, we can find the gamma decay for this 344 keV. So when europium-152 decays to the gadolinium-152, it goes to this excited state. This excited state is 344 keV above the ground state. It decays, and the percentage of the time, well, we have to find the percentage of the time with each decay. We multiply this number, 127.5, by 0.2085. We get that, so for every decay, there's a certain percentage that will show this gamma line, and we can find that information. As we see, we need to convert this data to percentage by multiplying by this factor. If you remember, we talked about this with the table of the isotopes for other data. Now we've evaluated one of the gamma lines, so there's still 2 of these 3 most common gamma lines for europium-152 decay we'd like to evaluate. If we look at the data for the 121.8 keV, we see that the data, the percentage is 1,362 times 0.02087. That decay is from this excited state of europium to this excited state of the samarium 152. So this is decaying by electron capture. Now the final data we need is for this 1408. The data that we can find from the table of the isotopes is listed here. So 1,000 times this number gives us the percentage. And the 1408 is actually shown on another decay scheme. If you see this decay scheme, goes up to 1371. If we want to go to 1408, we definitely have to get that, at least that excited above the ground state. So as you can see, for the europium-152, there's a lot of extra data that could make the evaluation and determination of the percentage of the decays a little bit less than straightforward. Another route to find these gamma decays, a little bit more straightforward method, is to search for them on these websites that are listed here. Both these sites here access the same databases. And what you need to do is go to these web pages. You can enter the element either by Z or by the symbol and the isotope, and data will come out such as what's shown here. You can also, if you have an Android, there's a browser that's available, and this is from the IAEA. I've put the link for that browser here, so you can also download that on your Android browser. So as opposed to the method with the table of the isotopes where you need to look at the data for each decay route, so electron capture and beta decay, with these databases, all you need to do is put in the isotope that you're interested in finding the gamma intensities for, and it'll provide the gamma intensities. And we'll look at these. So for instance, with the europium-152 example that we've gone through, here's the data for 121.8 keV. And what I wanted to point out is that there's 2 values for the decay of 121.8. And you can see that one of these values is for the metastable state and one's for the ground state. So we're interested in europium-152 from the ground state, so make sure you select the ground state data, which is here. And as you can see, that percentage is 28.58%. So 28.58% of the time, when europium-152 decays, you'll see a gamma at 121.8 keV. The next example is for 1408 keV, which is shown here. This is fairly straightforward, and we see that the data is 21%. And then finally, the last photo peak that we were looking at was the 344.3 keV. And again, we have two of the exact same values. We see that one is from the metastable state, one's from the ground state. We're interested in the ground state, and we see that that value is 26.5. So we make sure we select that one. We have 26.5. And these values are much easier to find. Now the table that I'm showing here is actually just a smaller version of the entire data that you'll get for the gammas from europium-152. But as you can see, compared to the table of the isotope data, to find these percentages for the gamma intensities, this is a much more straightforward method. When nuclei decay by alpha or beta processes,
the transition from the parent to the progeny isotope can leave the progeny in an excited nuclear state.
And if it emits this electromagnetic radiation, a photon, we call that gamma decay. However, there are other routes that are accessible for this de-excitation. If the de-excitation is from a very high energy state, generally well above 1 MeV,
pair production can occur. This is the creation of a positron and an electron from the excess energy. Since the energy of each is 0.511 MeV, it is necessary that the energy is above 1 MeV.
There's also a route, and this is particularly dependent upon the spin and parity between the excited and the ground state, where internal conversions from the interactions between the nucleus and the atomic electrons can occur. So this is internal conversion electrons, where atomic electrons are emitted. The energy of their emission is based upon the difference between the nuclear excited state and the binding energy of the electron. So for some of these transitions, we've already discussed gamma decay or the photon emission. Let's talk about pair production, where if it exceeds 1 MeV, this is a relatively uncommon mode. We'll discuss some routes in which it's achievable. But the emitted energy with kinetic energies that total the excitation energy minus 1 MeV. So the energy, this 1 MeV, goes into producing both matter electron and antimatter positron. Generally speaking, gamma decay is characterized by a change in energy without the change in the Z or the A. These transitions that we're talking about, these gamma transitions, tend to have very short lifetimes, and we can see this on the table of the isotopes, where the half-lives of those transitions are labeled, generally on the order of picoseconds. Anything that's longer lived, anywhere from many microseconds to days, even years, can be metastable states. Now, these gamma transitions that we see in the table of the isotopes are used for determining nuclear energy level and gamma decay schemes. Now, similar to alpha and beta decay, recoil occurs from gamma decay. So this recoil, we can have equations that describe the recoil. So the recoil energy is listed here. When a simple equation is the recoil's energy is equal to the square of the gamma decay energy divided by twice the mass. This energy's in MeV. And as an example, if we have a 2 MeV photon and an A of 50, we can see that there's a recoil energy of 40 eV. We use our conversion between MeV and AMU to determine this value. Now, this doesn't seem like a very large value, but it's actually the basis of Moessbauer spectroscopy, which we'll discuss starting on page 19. And as another example, if you look at a rather large de-excitation, a 15 MeV photon emitted from carbon-12, you can see that you can have a very large excitation from this state. Similar to what we described with alpha decay, and particularly with beta decay, there are selection rules for gamma decay. These selection rules can be based upon electromagnetic forces. Since the photon radiation arises from electromagnetic effects, it can be thought of as a change in the charge and current distribution in the nucleus. And if we think about charges and currents, we can talk about these distributions in terms of electric moments, if the charge distribution, or if there's a change in current, that could be thought of as a magnetic moment. So we can describe gamma decay as either magnetic, if it has to do, if it's yielding from change in currents, or electronic, if it's change in charge. And we're going to go over some rules that talk about spin and parity related transitions and how that can be used to classify whether a decay is magnetic or electric, M or E. We're also going to discuss the polarity as it relates to magnetic and electric distributions of gamma decay. So monopole, quadrupole, etc. One of the things we are going to see is that the transition probabilities decrease rapidly with increasing angular momentum. So changes that occur, if they have large spin and parity changes, the probability is going to decrease, just as we've seen with beta decay. And if we go to the table of the isotopes, we'll actually see that the transitions, such as the one listed here in E2, is shown for the certain gamma transitions for the decay. So for instance, here's this decay state that we looked at before, for europium 152. And we can see the energies of the transitions and their classification of an E2 transition. And we'll just explain that in a little bit more detail in the upcoming slides. So we can describe the angular momentum from the gamma decay being the L of 1, 2, 3, 4, etc. as a pole. So an L of 1 be a dipole, quadrupole, 2 to the 2 is 4, octopole, etc. Shorthand notation for electric or magnetic 2 to the L pole is written as E1, or excuse me, EL or ML. So for instance, an E2 we'll call an electric quadrupole. And those are shown over here. We have an E1 is electric dipole, and M1 is magnetic dipole. E2 is an electric quadrupole, M2 magnetic quadrupole, etc. Now there's routes where we can determine the multipole of the decay. And all we're going to do is look at the spin and parity of the initial and the final state. So here we have the spin and parity of the initial state and the spin and parity of the final state. We can use this to determine the angular momentum of the decay, which will be used to evaluate what this polarity is. So basically, the polarity can run from the sum and the difference of the initial and final state. If the initial and final state have the same parity, the allowed transitions are even L electric multipoles and odd L magnetic multipoles. And if the initial and final states of this gamma transition are in different parities, the electric multipoles are of odd L and the magnetic multipoles are of even L. So let's go through an example, or two examples, that demonstrates this. Let's assume that there's a gamma transition from an excited state of 4 plus to a ground state of 2 plus. So if we go back over here, the angular momentum will run from the sum and the difference of these values. So 4 plus 2 is 6, 4 minus 2 is 2. So L will be between 2 and 6, so it'll be 2, 3, 4, 5, and 6. The parities are the same. So we go here, initial and final states have the same same parity. Magnetic multipoles will be even. Electric multipoles will be even. Magnetic multipoles will be odd. So if we go from 2 to 6, magnetic multipoles are even. So 2 will be an E, E2, M3, E4, M5, E6. Those are the allowed transitions, and generally speaking, the lowest multipole transition will be observed. So one would expect to see an E2, so an electric quadrupole transition observed. And we can see here the electric quadrupole will have a spin change of 2, which is what we predict, and no parity change. So we can actually get this out of the table. So again here's another table where we have an electric quadrupole, spin change 2, no parity change. Now we can look at another example, cesium-137. We can pull this out of the table of the isotopes. The cesium-137, the gamma decay, it goes from the 11/2 state to 11/2 minus to the 3/2 plus. So 11/2 plus 3/2 is 7. 11/2 minus 3/2 is 4. The states are of different parity. So the electric multipoles will be odd L, and the magnetic multipoles will be even L. It goes through 4, so the magnetic, so it'll be M4, E5, M6, E7. And as we saw, M4 is the lowest, and that's the value that's listed right here on the table of the isotopes. Another decay route we've discussed is isomeric transition, and this is just the photon emission from an isomeric state or an excited nuclear state. There are routes for determining the probabilities of these transitions. The probabilities are based upon the energy and the A and the L. And fundamentally, what this says is for a given spin change, the half-life of this isomeric state decreases rapidly with increasing A and even more rapidly with increasing E. There's models called the Weisskopf single particle models, which are used to predict low-lying states. And they can be used to evaluate the expected half-lives of these isomeric states. Examples are shown here on this table where we can evaluate a partial half-life based upon the A and the E. These are for different transitions, so the L is built into the transition types. And we can use these values, these partial half-life calculations, to estimate the expected gamma transitions based upon, in this case, an A of 125 and an energy of 0.1 MeV. And we see that, and this is in seconds, and we see for these allowed transitions, we have very short-lived states. In E1 is 10 to the minus 13, and M1 is 10 to the minus 11. Whereas if we have high transitions, these half-lives can be, an M4 for instance would be almost 10 to the 10th seconds, and E4 would be again on the order of 10 to the 8th seconds. So these would be very observable metastable states for these isomeric transitions. These models can be used to evaluate these islands of isomerism, which are seen on the chart of the nuclides, where areas have large degree of isomers for given elements. For nuclei in excited states that are at 0 plus excited states, it's possible to have a de-excitation of that nuclear excited state without the emission of a photon. So there are a few non-photon emissions for de-excitations. As an example, here's a part of the nuclear excited state for germanium-72. And as we can see that there's this 0 plus state that's shown. The transition from that excited 0 plus state to the ground state cannot take place by photon emission, because for a photon it has spin and therefore must remove at least 1 unit of angular momentum. 0 to 0 transitions, there are no units of angular momentum lost. And if no change in parity occurs, de-excitation must occur by other means. For instance, for this example with the germanium-72, this de-excitation occurs by internal conversion electrons. So that energy, which is around 600 keV, or 691 keV above the ground state, results in the emission of electrons, atomic electrons, with that energy. And then here's an example of calcium-42, oxygen-16 has the same, where the energy is shown here at 1,837 keV above the ground state. That's larger than what's necessary for pair production. So this de-excitation can occur by pair production. For the internal conversion electrons, there are some methods for evaluating, particularly internal conversion coefficients. When this de-excitation occurs, generally speaking, K shell electrons are emitted. This emission is usually with some discrete energy. It can often occur only with one particle. Now there's an internal conversion coefficient, this alpha term, which is the ratio of the rate of internal conversion processes to gamma emission. So the internal conversion process divided by the gamma emission rates. As we see, these values are listed here, and they range from 5 times 10 to the minus 2 to something on the order of 2 times 10 to the second. The way the numbers are explained are listed here. So as we see some trends, as we go up, for example, let's inspect Z of 30, transition types E's. As we increase in the transition type from E1 to E4, this coefficient increases. Same thing for the M's. And for a given transition type, let's inspect N4. As we increase in energy, we see a decrease in that transition, everywhere from 100 to 1,000 keV. The second term, this K over L, that's just the K to L electron. That's the conversion ratio. That's the ratio of K electrons to L electrons involved in these internal conversion coefficients. And you see there's also trends related to which you'll have the K or the L, where it increases, or it's high at low E transitions and decreases with higher transitions. And the same through inspection, we can see that for the E and M types for both Z of 30 and 50. Now these internal conversion electrons can show up on beta spectra. And here's an example of 2 peaks where we can see for Mercury 198 and Mercury 203, where we'll have beta electrons, and then on top of those spectra we'll see the internal conversion electrons, and we see the K, the L, the M. From this we can get the K to L ratios, and if we look back on the chart on the previous page, if we know something about the K to L ratio, we can figure out information about the multiple order. So that'll give us information on change of spin and change of parity involved in these processes. One aspect of gamma decay that we discussed are these multipole interactions, both electronic and magnetic. And there's the assumption that the gamma rays have no track of the multiple interactions from the productions. In other words, there's no correlation between the behavior of the gamma rays and as they're emitted from the nucleus and their multipolarity. In some cases, you would expect these multiple fields to give rise to angular distributions that are related to the direction of any angular properties within the nucleus. This is generally not observed during gamma decay, and even if it was observable, since most nuclei are randomly orientated, if there were any correlations with gamma decay, those would also be randomly orientated. This would be removed if samples of nuclei could be aligned and then the gamma array orientation observed with respect to this alignment. So one can align nuclei by placing them in a magnetic or electric field at low temperature, something close to 0 K, so vibrations would also be limited. You can observe the gamma ray in coincidence with the preceding radiation, either an alpha, beta, or even another gamma. Think about the gamma cascades that you could observe from europium-152. And there should be an equation that describes the correlation. Its correlation function is listed here. So basically, if I had a detector, for instance, that could see two gammas, I should be able to see a rate as a function of angle between the two detectors. And this the rate as a function of angle should be able to be plotted and will be based upon the multiple characteristic of the gamma radiation emitted. An example of this is shown here, where we need to correlate gamma emission with the preceding radiation. We need very short lifetimes, so no metastable states. And we need to be able to measure coincidence as a function of an angle, so this theta. So imagine if we had some sort of schematic diagram where a gamma is emitted, it occupies a state, and that gamma then goes to another state. So we should be able to correlate one gamma with an energy feeding another gamma that has another energy. And if I look here, depending upon, as I went from this state down to here, 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 I would have three different energies, and correlated with those would be three different energies. Within the nucleus, it would look like this. Imagine I have my nucleus aligned. One gamma comes out of one state, and the second gamma, since it has certain multipole and magnetic or electronic configuration, would have a certain correlation from that initial state. The data would look like this. This W theta, which I would get from the previous equation, as a function of angle. So I'd be able to use this correlation to determine the multiplicity of the state of the gamma decay. This requires a cascade, and the z-axis would be defined by the first gamma emission.
This concludes part 1 of lecture 6 on gamma decay. When you've completed this lecture, please continue to part 2.